We're looking at scientific notation today. This is going to be really interesting. It's a new way of understanding numbers, different than what we've been traditionally doing here. So traditionally, we might take a number like, say, the number 12 right here. That's a great number. I love the number 12. We can consider this discrete quantity, this 12, this number to be sort of constructed of prime numbers that you multiply together. The prime factorization here would be 2 squared times 3, right? So 2 times 2 times 3, that gives you 12. These are sort of like the elements in number theory. These are the components that you multiply together to get all of the other numbers that can possibly exist, all of the other natural numbers like the number 12, right? That makes sense. We could also think of the number 12 as a rational number. In that case, it can be composed of a ratio of integers. In this case, 12 over 1. That's a ratio of integers. It's going to be equivalent to 24 over 2 or 36 over 3, or sort of have an endless number of possible representations that are equivalent to the number 12, right? Rational numbers. We talked about that in a previous lesson. We could even look at a number like the square root of 2, right? We could sort of see where this comes from, like a geometric representation. If you have like a right triangle like this, if these two sides are length 1, then using the Pythagorean theorem, a squared plus b squared equals c squared, well then c must equal the square root of a squared plus b squared. So square root of 1 plus 1 would be the square root of 2. That must be the length of this side. But the thing with the square root of 2 is this is an irrational number. If we try to write out the decimal expansion here, we would get something like 1.14142, and it would keep on going forever, right? You could keep writing digits here and never completely write down what would be equivalent to the square root of 2. But you get closer and closer, right? So there's this idea, there's this concept that the square root of 2, this irrational number, has a very specific exact value that we can approach as we keep, writing more terms on and towards infinity. Scientific notation's different, okay? It's going to make us think about numbers in a different way because numbers in the real world don't act like this. Let me give you an example. What if I ask you a question? Okay, let me ask you a question. How old are you? That's the question. How old are you? Think about it. And whatever number you thought of, I'm telling you, you're wrong. You are not that age. Why are you not that age? Well, let's imagine you are 12 years old, okay? If you're 12 years old, maybe you're not, maybe you're 32, 42, 62, whatever the age is, whatever the age you thought of, when you say you are something like 12 years old, that's not exactly true, is it? Like, is today your birthday? Were you born this day 12 years ago? Probably not, right? Today's probably not your birthday. And so whatever number you thought of, well, actually, you're more than that. You're older than that. You're not exactly 12 years old. And even if today was your birthday, were you born, at this time, this hour, this minute, this millisecond, 12 years ago, or however many years ago? Probably not, right? Because by the time I finish speaking this word, that time has passed, and so now even if you were before, you're not anymore exactly 12 years old. So this number is not actually correct. Instead, what we really mean is you're 12-ish, right? You're approximately 12 years old, not exactly 12 years old. In fact, what we're probably saying is that you're 12 and a half plus or minus 0.5 years old, right? That's actually what we're talking about. Anytime somebody gives an age, they're implicitly giving you a range of ages within sort of 1 year. And so this is how numbers work in the real world. We can't just say, you're 12 years old, well, you must be 2 squared times 3 years old, right? The prime factorization doesn't work that way because we don't really mean exactly 12. We mean 12-ish. We mean approximately. And so that's how actually numbers work in the real world. In the real world, numbers are approximations. We don't work with them like this or like this, representing some exact quantity. Scientific notation is going to help us explain and represent that more accurately. Even some other numbers that you might think are exact in the real world, turns out they're not exactly exact. Like, for example, countable objects are usually seen as having an exact number. Like, how many cars does your family have? Let's say your family has 2 cars, okay? Seems like an exact number, right? You open the door, go outside, there's 1 car, there's 2 cars, that's it, right? But we can actually think of this in different ways. For example, what if I'm saying not your family, but I want to know your country or your city or your region, how many cars are in your country, right? Maybe try and count them up, you get something like 10.2 million cars in your country or wherever, your region. And notice how I wrote this. I wrote 10.2 million, right? But that's not an exact number to the individual car, is it, right? In fact, if I wanted an individual number, I'd have to write something like 10,214,363, right? Now, here's an exact number. But if you think about it, does it even make sense to write a number like this for the number of cars in your country, right? Or in your city? Because cars are sort of coming in and leaving your country all the time. New cars are being bought, old cars are being sold, imports, exports. New cars are being built, right? They're built out of pieces. Old cars are getting into accidents. They're being wrecked. They're disappearing. Cars are being taken apart, put back together. What we kind of have here is we have a flux of cars. And so maybe you have hundreds or even thousands of cars every day being made, being sold, coming in, going out. And so it doesn't really make sense to deal with all of the numbers that you have over here because they won't actually be that precise. You can't have an accurate number that way because of this random flux of cars that you're getting day by day, hour by hour, minute by minute. The exact number is changing. And so we can only be so precise. To go to the individual cars too much. In fact, you could even take this further, right? You could imagine that, maybe you have a car at home, you have 2 cars, but maybe one of them gets into an accident. You gotta get it fixed. You take the 4 wheels off. It can't drive anymore. Does it still count as a car, right? What if the engine's malfunction? You take the engine out. You're gonna have to fix that. So now your car, what has no wheels, has no engine, it's just sitting there on blocks. Is that really a car? Do you still have 2 cars in your family? Or is it less than 2, right? Is it a fraction of a car? How do we count that? What if the mechanic says, sorry, I can't fix the engine, it's busted, you better just can't do anything with it, it's unfixable, right? Well now, once he says that, now do you say you no longer have that car? Right? It's ambiguous. Even countable objects like cars or people or whatever gets a little bit hazy, gets a little bit into the weeds, into the philosophy of existence, of being, what counts as being a member of one of these sort of categories of things that humans have invented. Not always perfectly clear. But this is sort of getting us to the idea of scientific notation, how we're actually going to describe things when we treat numbers as approximations. So let's take a look at how we use scientific notation. So what we've got here is a formula that describes how you can write down some number x in this scientific notation form. And it's a little complicated, it's not too bad, right? Basically, you'll have some number a. A is going to be less than 10, but greater than or equal to 1. And then it'll be multiplied by some power of 10, right, where this n is an integer. Let me show you how this works. Okay, so let's go back to the idea of the number of cars in your country, okay? We said that there were 10.2 million cars, right? Now, if I was to just write this out as sort of a normal decimal number, I would write 10,200,000. That's what 10.2 million means, right? And if I was to write this now in scientific notation, what I would write is 1.02 times 10 to the 7. Okay, that is an equivalent representation to this number right there, right? Essentially, you're going to have to move. If I have a 1.02 times 10 to the 7, it's like I'm taking this and moving the decimal point over 1, 2, 3, 4, 5, 6, 7 spaces. Okay, that's what this power of 10 is going to allow me to do. Let me show you how this scientific notation best explains the approximation that this number really is representing. We started with 10.2 million. With nothing else afterwards. And so it turns out that actually these zeros are not exactly zeros. Because we don't know what these numbers are, right? This zero here could be a 0, or maybe it could be a 5, or it could be a 2, right? Same thing over here. What does this digit actually represent if you were to count down to the individual car? Well, it's probably not a 0. And so it turns out that these zeros are placeholders. It would actually be better if instead of writing zeros, we had some other character that we could write in here to represent the placeholder that this space is holding. It's not a 0. We don't know what it is, right? What we do know is we know that this is a 2, this is a 0, and this is a 1. These numbers are meaningful, right? You might even call them significant, right? So this goes into the whole idea of significant figures that I'll talk about in another video. But when you write it down in scientific notation, you don't write those meaningless numbers down. You only write down the digits that have real meaning, that represent real information that you measured. And so in that way, scientific notation eliminates the ambiguity you get by writing down all of these zeros in large numbers like that. And the other thing scientific notation does is it gives you this power of 10. And that's a very powerful way to write very, very large or even very, very small numbers and write them compactly in a very concise and easy way. This 10 to the 7 gives you an order of magnitude. It tells you right away how big roughly this number is going to be. And so that's sort of the key with scientific notation, right? It's going to allow you to write down approximate numbers while being explicit about how good that number is, how well you've measured it. And then it allows you to compact down very large or very small numbers. So let me give you an example. Here's another scientific number written in scientific notation. How about 5.16 times 10 to the 11, okay? If I was to write this down in a full decimal expansion, well, I'd have to write a 5, and then I need 11 places, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay? Comma here, comma here, comma here. We can see that what this number actually represents is 516 billion, right? That's a big number. Writing it down this way, that's a lot of zeros. That's not great to be writing down. Easy to make a mistake, easy to add an extra or forget 1 0. You mess up the whole number. Much better to write it in scientific notation where we see clearly that we have 3 meaningful digits here, and the size is an order magnitude of 10 to the 11, right? Very clear. Let's do one more. How about 2.904 times 10 to the negative 6? Okay, again, if I was to sort of expand this out, what would I get? Well, I would get, I need 0.123456604. That's exactly what I would get in the decimal representation. And this is hard to look at. It's hard to see actually how big this is. Much better to look over here and say, oh, it's about 10 to the negative 6. It's about a millionth of whatever this unit is, right? Much easier to see it this way. Notice how we found this, okay? So what we did here is by multiplying by 10 to the 11th, you're going to take whatever this decimal point was and move it over 11 places, okay? We moved it to the right 11 places to convert to a decimal notation. And now for this one's a negative number. So actually what we did is we moved the decimal point. It used to be here, and then we moved it to the left 6 places, okay? And so that's how we can convert between a decimal expansion and scientific notation. Let's look at a few calculations. We'll see scientific notation makes calculations easier as well. All right, so here's 3 numbers. We've got an A, a B, and a C, and we want to multiply A times B and then divide by C. Okay, so how do we do that? Well, what I'm going to do is I'm going to write each number in scientific notation first. So for A, I'm going to say that's the same as 5.76 times 10 to the negative something, right? So this is going to be 1, 2, 3, 4, 5. 10 to the negative 5. And then for B, I'm going to represent that as 1.5403 times 10 to the, what's that going to be? So I'm already at 3. And then I'm going to have to go 4, 5, 6, 7. Okay, so 10 to the 7. That's what b is. And then I'm going to divide this. I'm going to divide this all by c. Now, c is actually already written in scientific notation. So that's easy. I'll just 4.12 times 10 to the negative 8. Okay, there we go. Now what I can do is I can actually treat each of these as a separate term that you're being multiplied together, right? This power of 10 to the negative 5, I can move that around. Multiplication is commutative. And so I'm going to rearrange everything on the top. And I'm going to say that's equal to 5.76 times 1.5403 divided by 4.12. I'm going to have that multiplied by, well, here I have a 10 to the negative 5 times a 10 to the 7 divided by a 10 to the negative 8, right? But this entire thing, I can condense this. I can take this entire thing here, and I can convert this into, what's this going to be? This is going to be 10 to the minus 5 plus 7, and then if I take this and I bring it up to the numerator, it's going to be a plus 8. Using my exponent rules, I can see that this is going to be equal to 10 to the power of, well, it's going to be 10, right? 10 to the 10th power. So that removes all of the magnitude. The size is going to be 10 to the 10. Very easy to calculate. And then I just have to plug this into a calculator. Let me do that. All right, so what do I have? 5.76 times 1.5403 divided by 4.12. What do I get? Okay, a really long decimal here. I'm just going to round this off to 2.15. Later on, we'll learn about some of the rules about how better to round that. But 2.15 is what I get here. And then that's all multiplied by 10 to the power of 10. Okay, so there we go. That's actually the final answer here. And you see how easy it was to do that when you can rip away the magnitude and just treat those powers of 10 as multiplying and dividing together. Then you just have to deal with this right here. If I had to type in all of the zeros here, or all of these digits plus another 3 zeros, and then, 7 or 8 more zeros over here, easy to make a mistake. Maybe it won't even fit in your calculator, right? So using scientific notation makes these calculations a lot easier. Okay, so hopefully this was a good introduction to scientific notation. And next lesson, we're going to look more in detail at significant figures. So I'll see you there.